Hello everyone, welcome to Taylor's Classical Mechanics. This is problem 4.3 from the book. So we're going to go ahead and kind of just dive in here. So this problem is going to be very similar to problem 4.2. So we're just going to get some more practice doing these line integrals. And it's going to be, the force though is going to be different. So the force is going to be negative y x hat plus y hat. And now the three paths that we got to integrate over are these paths defined by this right figure here. So the first path is going to go from P here, starting at 1, 0, going to the origin, and then up along the y-axis to the point Q. So that's our first path we got to integrate across. Our second path is going to be this line going from P to Q, this straight line. So we just got to figure out how to define that line. Then the third path is going to be this line here, which is this quarter half, this right quarter of a circle that would be centered on the origin O. So, you know, we know the definition of a circle, so we can find some way to define this curve and integrate across it. So let's go ahead and take a look at our problem. So again, I just drew a rough sketch here of the figure. I wrote down the force, which is minus y x hat plus x y hat. Now for the first path, right, we kind of have to split it up into two different paths. So we're gonna have two different integrals, one from P to O, then from O to Q. And along the first path, y is 0, and along the second path, though, x is 0, right? We're only on the y-axis. So what we're going to end up having here is that if you do f dot dr, we get minus y dx plus x dy, right? Where dr, if you don't remember, dr is dx x hat plus dy y hat, right? Just a differential amount of length, at least in Cartesian coordinates, which we're working in here. And if you do this integral, well, the integral of this, y is constant along this path. So you just get minus yx evaluated from 1 to 0. And then the second integral here, x is constant. So you get xy evaluated from y equals 0 to 1. But if you plug in what y and x are for each of those paths, well, y is 0 along the first path. So this whole term is 0. And then the second term, x is 0 along this path. So this whole term evaluates as 0. So the whole thing is 0. And we end up just getting 0 work done across the first path. So nice and easy for that one. All right. For path B, right? For path B, this line, if you look, is essentially just like the line, excuse me, is essentially the line. It's kind of like y equals negative x, except it's shifted up by 1, right? So if we started from the origin and went like down, that would be y equals to negative x. But it's as if we shifted that line up 1. So really, the equation of that line is just y equals to negative x plus 1, right? Plus 1 since we're shifting the line up. And then dy then is just going to be equal to negative dx. And we're just going to rewrite this integral in terms of x, right? We could write it all in y. It's your choice, but I'm going to rewrite it all in terms of x. So if we take the integral from P to Q of f dot dr, we get minus y dx plus x dy. And we plug in our substitutions to get everything in terms of x. We get the integral from x equals 1 to 0, right? Because we're starting at 1 for x and we're going to 0. We get x minus 1, which is negative y, right? This is y, but it's negative y, so it's x minus 1. And then dx minus x dx. So dy is just minus dx, so that's why we get the minus x dx here. So then we do this, you just kind of distribute terms out, we get x minus 1 minus x. Well, that means that the x is going to cancel, so we end up just getting minus 1 dx and we're integrating that from 1 to 0, so we just get negative x evaluated from 1 to 0. So that's 0 minus negative 1, plugging in the bounds, and that's just 1. So the work done across that second path there is just 1. And that's different than the first path. So this force is also not conservative, meaning it's not path independent. Just a note. Now, for the third path, where we have this circle, where we're integrating across the circle, part of a circle, we can define a circle. This is a unit circle essentially, because the radius is 1, and we can define. We know how to express x and y in terms of an angle phi, like this polar angle phi. So on a unit circle, x is equal to cosine of phi, and y is equal to sine of phi. And so we can maybe just turn this into a polar integral, where we're integrating of phi over phi, where phi starts at 0, this angle, and then we're integrating to pi over 2. So we're going to try that. So here I write down that x is equal to cosine phi, y is equal to sine of phi. That means dx is negative sine phi, and dy is cosine phi d phi, just taking the derivatives of each of those with respect to phi. So then our integral from p to q of negative y dx plus x dy, right? That's just f dot dr. Now we can start plugging our substitutions, though, to get this all in terms of phi. So we get minus sine phi times minus sine phi d phi plus cosine squared of phi here, and then dy is just cosine. We get cosine phi times cosine phi d phi, so I just made that cosine squared of phi d phi. Then doing some more stuff, we get sine squared of phi plus cosine squared of phi d phi. Well, this is a trigonometric identity. Sine squared plus cosine squared of phi is just 1, and our bounds are still 0 to pi over 2. So really, we're just integrating d phi from phi equals 0 to phi equals pi over 2, which is just phi. And when you plug in the bounds, you just get pi over 2. So pretty simple once you get that kind of in terms of phi. And yeah, that's our third integral. So the work is different across all three paths. It's not a conservative force. It's definitely path dependent, the work done. But yeah, if you guys have any comments, questions, concerns, feel free to let me know in the comments below. Again, if you are new to my channel, I post solutions to tons of different physics problems. I'm doing Griffiths. Right now I'm doing Taylor's Classical Mechanics. So yeah, if you guys want the written solutions, you guys can subscribe to my Patreon and get them there. Otherwise, yeah, I'll see you guys on the next video, and see you guys later.